Hey everyone, and today we're going to be doing binomial expansion theorem, or just binomial expansion. So let's get started with the general term, a plus b to the n. What does that mean? Well, if we set n equals to 2, we would have, that looks like a z, but whatever, a plus b squared. And contrary to, like the meme, the big math meme, this does not equal a squared plus b squared. This instead equals a squared plus 2ab plus b squared. Now, this is because you take this and you multiply it by itself twice, or rather, I guess one time. So you would have a plus b times a plus b. And of course, you drag these out, bam, you get a squared. Do this, you get ab. Do that again, you get another ab. Do that one more time, and you get b squared. Now, two ab's, so of course you get 2ab, and then you got b squared and your a squared. So that's why you get a squared plus 2ab plus b squared, and not a squared plus b squared. Now, this is all fine and dandy, and that's super cool, but for higher and higher powers, this is super cumbersome. Like, for instance, if we wanted to raise it to, say, the 7th power, or the 5th power, 6th power, whatever it is, you don't want to write this out 5 times, or however many times, and multiply them all out and do FOIL, which is the method I was using there. So, instead, we have Pascal's triangle. So, of course, if we raise it to the 0th power, we would just have 1. Now, first power, a plus b to the first is just a plus b. And these are indicative of their coefficients. So, of course, a to the first plus b to the first is just a plus b. However, we see at the second power, when n is equal to 2, we get 1. So the coefficient here of a squared is just 1 a squared. But then in the middle, we have 2ab, and then 1 again, 1b squared. Now you'll notice as we go from the second to the third row, we add. So we have 1 plus 0, there's nothing here, it's just 1. But 1 plus 2 is 3, 1 plus 2 is still 3, and then 1 again. So this is for the third row. So instead of it being a squared plus 2ab plus b squared, it would actually be a cubed plus 3a squared b plus 3a b squared plus b cubed. And so on and so forth. We can see in the fourth row, we go 1, and then we add 1 plus 3, we get 4, 3 plus 3 is 6, 3 plus 1 is 4 again, and then 1 and 1. And as we escalate the higher and higher powers, we can continue this pattern. So for Pascal's triangle, this is great. You could expand out really easily. You know your coefficients, but this only works if your coefficients are 1. In the binomial you're expanding, a plus b, the coefficients are automatically set to 1. So what happens if you have something that's not 1? For instance, what if you had 3a plus b squared? Well, let's write that out. So we have 3a plus b squared. Now, obviously, this isn't going to equal a squared plus 2ab plus b squared, because we have a coefficient of 3 in front of the a. What this will actually equal is similar to this. However, instead of plugging in just a squared, we actually plug in 3a. So we would plug in 3a, and then we square the whole term. Then, instead of plugging 2ab, we would plug in 2 times a times b. In this case, a, we can set that to be 3a, and then b is still b. And then, similarly, since b is just, b, we can leave that as b squared. And when we simplify this out, let's say 3 squared is 9. We have 9 times a squared plus 2 times 3ab. This actually gets us 6ab. And then we would just have b squared at the end. So generally speaking, I wrote out the general term for a plus b squared because when you have a coefficient in front of your binomial for whatever term, you can simply plug in that term plus its coefficient into the generalized version. So in this case, I plugged in 3a for a squared, and 3a for a here to be able to get 9a squared plus 6ab plus b squared. And that is true for all, for higher and higher powers. It doesn't really change. You can still just plug in whatever term you have into the generalized version given by Pascal's triangle, multiply it out, and you get your answer. Now that's cool, but let's consider a case where it is not a plus b squared, a plus b squared, but rather a minus b squared. What happens then? So let's do that. When we have a subtraction term, so we'll just do a minus b squared. When we have a subtraction term, the signs alternate. So a times a is still going to be a squared, but because this is a positive a squared, the next sign is going to be a negative. So it's going to be minus 2ab. And then since this term is negative, the next term will be positive, so we will still have plus b squared. This is the generalized version. And of course, if you had coefficients, you can plug in those coefficients just like we did earlier. So I'm going to do the exact same example, except this time it's going to be its conjugate. It's just going to be a subtraction version. So it's 3a minus b squared. Now we can just plug in 3a for a squared here. So we get 9a squared once again. However, because it is minus 2ab instead of plus 2ab, it's going to be minus 6ab when we plug it in. Remember, 3 times 2, 6, and then uses ab. And then, once again, b squared is still positive, because even if we took negative b, squaring that will still output a positive, so it'll still be plus b squared. And as you can see, our signs alternate. It's a positive 9a squared, and then minus 6ab, and then once again a positive b squared. So though there's some of the basics for binomial, we have multiplying out binomials when their coefficients aren't the same, when their coefficients aren't 1, multiplying when their signs are either positive or negative. And generally speaking, even if, for instance, let's say b was a constant, let's say it was 3a minus 7, you would still plug in 7 for b squared, and eventually you would get 49 at the end. You don't have to necessarily have two variables. You can simply plug in those numbers into what the corresponding term of your expanded binomial and get out your actual answer. I hope that makes a little bit of sense. You could just, I don't know, do an example or something. Making this video a little lazily. Big procrastination on this one. But let's keep going on. For finding specific terms. So, what happens if we want to find a specific term? Typically, when we expand to really, really high powers, we're not going to need or rather, they're not going to be asking you, expand 2a minus 4b to the 7th, expand that fully, because raising something to the 7th power, a binomial to the 7th power, is absolutely awful to do out, and I would not recommend it. So instead, what they'll typically do is ask you for a specific term. So let's write out an example. So let's say we have 2a minus 4b. This is going to be raised to the 7th. Now, this is, looking at this, that's pretty scary. We don't want to write this out 7 times and do the FOIL out, unless you have an incessantly high amount of time. So instead, we're going to be finding the 5th term. Now, how do we do that? Now, one thing I haven't discussed is the power. You can notice that with the first term, it's always a squared. Correlates to this being raised to the 2nd power, so we have the first term is a squared. However, the second term here, 2ab, we notice that a loses a power. It's now just a to the 1st. And now all of a sudden b gains a power. Beforehand, we didn't even have a b at all. It's like b to the 0, which is just 1. So now it's b to the 1st. And now, in our final term, it is now a to the 0, or just 1. And b gains another power. It becomes b squared. So you notice that as a loses its exponent, b gains its exponent. That's very important for finding the 5th term of this, because we know now what the power of the 5th term is going to be. We know it's going to involve a and b because it's not the final term. It's not going to be some b to the 7th. Rather, we know it's going to be a combination of those. If you notice, a squared plus b to the 0. If you add up their exponents, 2 plus 0 is 0. This one is b, or rather a to the first, b to the first, 1 plus 1 is 2. Of course, 2 plus 0 is still 2. So we know now that our exponents have to add up to the power we're raising the whole binomial to, which in this case is 7. And so for the fifth term, what we're going to use, instead of Pascal's triangle here, we're going to be using combinatorics. We're going to use combinations to find it. So we know now that obviously the exponents have to change. And the way we do that, and the way we do that to account for the coefficients also changing, is going to be we're going to use combinations. 7, choose 5. So we have a power of 7. We're trying to find the fifth term, so we do 7, choose 5. And now we do 2a. Now typically, if this was the first term, it would be 2a to the 7th. Now if we're doing the fifth term, we do 7 minus 2. So this becomes, 7 minus 5, which is 2. So we have 2a squared. And now, because it has to add up to 7, or our exponents have to add up to 7, we know the other term is going to be 5. Or raised to the fifth power. So minus 4b to the fifth. Now let's simplify this out. 7 choose 5 is simply 21. 21 times 2a squared, the whole thing squared, would be 4a squared. Now we're going to be doing negative 4 to the fifth, I believe comes out to minus 1024. And then of course we would still have b to the fifth. And now you can just do some number crunching, but this ultimately gets us, I'll write it up here. This ultimately gets us negative 86,016. A squared, of course don't forget those, b to the fifth. This is our fifth term of our binomial expanded to the seventh power. So in conclusion, in finality if you will, essentially with binomial expansion, you take some binomial, raise it to a power, you're multiplying it by itself that many times. A plus b squared is not a squared plus b squared, it is a squared plus 2ab plus b squared. And for finding specific terms, you would like to use combinatorics. So for instance, if we wanted to find the x, or if we raise some binomial to the nth power and we wanted to find the x term, generally would do x choose n, other way around, b, n choose x, of sum a to the n minus x times sum b to the x. And of course, this is a generalized version of how to find the specific term of a binomial, and this is Pascal's triangle for finding the coefficients of your binomial. Of course, if your coefficients in the binomial given are not 1, you would have to multiply it by these coefficients here, but that's relatively simple to do, and I leave that as an exercise to the reader, or I guess watcher and listener. So yeah, thank you for watching.